All right, and here we have one last example. This is with medication. So it says a hospital patient is required to have at least 84 units of drug A and 120 units of drug B each day. Now assume that overdoses are not harmful. All right. Each gram of substance M contains 10 units of A and 8 units of B, and each substance N contains 2 of A and 4 units of B. And suppose both M and N contain undesirable drug D, which is 3 units per milligram per gram in M and 1 in N. And so, how many grams of each substance, M and N, should be mixed to meet the minimum daily requirements of these values up here and simultaneously minimize the intake of drug D? So, we want to get as little drug D as possible, but we want to meet those minimum daily requirements. So, again, we can go over those limits, it doesn't kill them, but we don't want to go very high with the D. So, we're minimizing that D. And so how many units of the undesirable drug D actually will be in this mixture that we find? So first we have to construct our model. So we're going to say, okay, well, let X be the number of grams of M and Y for N. And we summarize all the stuff we just found. So drug A said 10 units per gram of M, 2 for N, and the minimum requirements for daily is going to be 84 units. For B, it was 8 units per gram for M, 4 for N, and 120 is daily minimum requirements. And substance M had 3 grams of D and 1 gram of N rather. And so those are going to be kind of our constraints that we're going to write into our problem. So again, X is M, Y is N. Makes it really confusing when we're changing one letter for another letter, but it'll work. All right. So we want to minimize the amount of drug D in the daily dose. So our objective function is C is equal to 3x plus y. Okay, 3x plus y. So the 3x plus 1y. That's going to be what we're trying to minimize. And our constraints are going to be, well, here we have to go back here, 10 and 2 and 8 and 4. 10 and 2, 8 and 4. And then our right side, that was going to be, has to be at least 84 units and it has to be at least 120 units. So those are those two items. Remember, X and Y have to be greater than or equal to 0 as well. So then we get the very last row here. And so that's going to be our actual model. So we're going to minimize C equals 3x plus y, subject to these two constraints plus the X and Y greater than or equal to 0 constraint. And we graph those. So we graph those items. It's going to be in the top right quadrant again. And so now what we have to do is, once we graph them, we have to find what those points are. And with those points, we make a table and we can minimize it. We can't maximize it, but we can minimize it. So we have to plug all those in to see what the values are going to be and which is going to minimize that D. So we plug in 0, 42, 422, and 15, 0, and the minimum one is going to be our 34. So that is going to be at the 422. So at this point here, that's going to be the minimum. And so that means we're going to use 4 grams of M and 22 grams of N, and that's going to be giving us a minimum dosage of the undesirable drug D of 34 units. And again, that 34 units came from right here. Okay. And so any other combination of M and N in the feasible region is going to result in a larger quantity of the undesirable drug D, which is not what we want. And so that's why we're minimizing the drug D. And again, we don't really care how much extra M or N we get. It's the D that we're really caring about in this problem. All right, so that's all I have for this section. Hopefully that will help.